Hello there, and welcome to the online materials of Machine Learning for Audio Signals in Python. This is a course offered by Professor Schule at the UMNL University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about the neural network basics, and we'll start looking at neural networks as detectors. So let's get started. The simplest layer is the so-called fully connected layer. If we have a one-dimensional input array X with a certain length, let's say the length is given by n features, and a one-dimensional output array Y of a certain length, and this length is given by out features, then the function of this fully connected layer is simply a matrix multiplication with an addition of an array B, that's called bias, followed by a nonlinear function called the activation function. In PyTorch, the matrix multiplication and addition is implemented in this function here. So the linear layer computes the function y is equals to x multiplied by A transpose plus B, where T here is the transpose operator for the matrix. The coefficients of the matrix A and the array B, they are called weights. So, and they will be obtained, these weights will be obtained by using optimization. That's also called training in neural networks terminology. You can take a look at this function in PyTorch. Looking at the PyTorch documentation, we have here this linear, and it applies a linear transformation to the incoming data y equals x times A transpose plus B. And here we see the in features, the out features, and the bias. So this is the size of each input sample, the size of each output sample, and bias here it can be set to false if we don't want to use bias, or it can be set to true, which is the default. This is called fully connected because the matrix A connects each input element, so also called feature, to each output element or feature. The input and output arrays, they are one-dimensional because of the full and fixed connectivity. If we have an image as an input, we will just have to reshape into a one-dimensional array, for instance using view or reshape in PyTorch. Often neural networks are used as detectors. In that case, each value in the output array Y would correspond to the output of one detector, and each detector represents one class. This linear layer is usually followed by a nonlinear function, also called an activation. For instance, the rectified linear unit function can be applied to each output element or feature. So this is also called the ReLU, the rectified linear unit function. This function applies the element-wise function given here. So this function limits the output to the non-negative range, and this is useful when the output represents a detector. In this case, a value of 1 might mean detected with certainty, and a value of 0 would mean not detected with certainty. Here, negative values would make no sense. This is probably the most often used activation function because of its simplicity. In PyTorch documentation, you can also take a look at the ReLU, and it applies this rectified linear unit function element-wise, given here, and we have all the documentation about this function. Often, a slightly modified version is used, which avoids the vanishing gradient for negative values, which helps the optimization. In this modified version, it has a small slope for negative values, and it's called the leaky ReLU. And we can also take a look at the PyTorch documentation of the leaky ReLU, and we see that there is a small slope here, and we can set these values So we can, there's negative slope, is a float that by default is 0.01. So we can change this, and this leaky relo will apply this function here. So we have this negative slope times the minimum of 0 to x. Another activation function is the softmax, and the softmax activation function turns the outputs of a network into looking like a probability function, positive and summing up to 1. So this is another very used activation function, and again we find in the documentation it's given by this equation here. This is the softmax, and this applies the softmax function to an n-dimensional input tensor, rescaling them so that the elements of the n-dimensional output tensor will lie in the range of 0 to 1 and will sum to 1. An alternative activation functions is the so-called sigmoid function, which is differential everywhere, but it's more complex to compute. This is the classic activation function, which is already used in the early papers about neural networks. And the sigmoid is given by this function here, and we find it. You can also look, see how it looks like in PyTorch documentation. We will now take a look at the Python example for a linear layer. So for a linear layer, the shape of the input and the output tensors are given here. So we have an input, given the shape is n star h in, where star means any number of additional dimensions and h in means the in features like we've seen before. The output has the shape n star and h out, where all but the last dimensions are the same shape as the input, and h out is the out features like we've seen before. Capital N is a batch size. Star is usually the index for the test set. H in is the length of our input signal, and h out is the number of classes or detectors that we desire. The edge index is for different sets of training and data. Optimization is performed one batch after the other. This saves memory because only one batch is loaded in memory. In our example, let's imagine that we have two input signals that we want to detect, one increasing and one decreasing. So we have here x0 is given by 1 and 2, and x1 is given by 2 and 1. We will assemble these two signals into a two-dimensional tensor, some matrix, where each signal is one row. So now we have this matrix called x, and here we have the x0, 1 and 2, here we have x1, 2 and 1. We want to have two detectors, one for the first signal and one for the second signal. The desired output of the first detector should be 1 for the first signal x0 and 0 for the second x1. On the other hand, the second detector should output 0 for the first signal x0 and 1 for the second signal x1. The desired output is also called target in deep learning, machine learning, neural networks nomenclature. We assemble the desired outputs for targets in a matrix where each detector corresponds to one row. So here we have the first detector. Like we've said before, it should be 1 and 0 for the first signal, and 0 and 1 for the second x1 signal. For our linear layer, we now need to find the weights or the coefficients of the matrix A and bias B such that the desired output Y is approximated given out the training set X. So we have that this matrix should be our input matrix X multiplied by A transpose plus B. This is a matrix of coefficients or weights. This is the bias. And in this simple case, we can actually find a closed form solution. So if bias is 0 and 0, and the A transpose is the inverted X times Y, then we have a closed form solution for this problem. If now we have more samples in our training set for X and Y, we will get tall matrices. For instance, we could add another input x2, for example, 1 and 1. For each, both outputs should be 0 as target. For the non-quadratic matrices, we can compute the pseudo-inverse, which minimizes the mean square error between the network output and the desired output. And it's given here in these equations. Observe that this does not include the bias array B, which might lead to better approximation and also needs the mean squared error. Depending on the application, we might want to use a different error measure, also called loss function. A simple and widely used loss function is the mentioned mean squared error loss. So PyTorch has this function implemented, as mean squared error loss. And for detectors of different classes, usually the so-called cross entropy loss is used. And it creates a distance or divergence function between two probability distributions. Here, the probability distributions are the target distribution, probability 1 for the true class and probability 0 for the false class, and the distribution that the neural network generates, a predicted probability for each class with high probability value for the class that the network thinks is at its input. In PyTorch, we have also this cross entropy loss, and you also find all the details in PyTorch documentation. To obtain a better solution and include other loss functions, in general, numerical optimization is used to find the weights of coefficients which minimizes a given loss function. Observe that the loss function produces a single number or value for a given training set and given weights. The weights are then updated during the optimization to reduce the loss function. Common optimizers are, for example, the stochastic gradient descent, SGD, and adaptive moments, ADAM. After we obtain the weights from the optimization, we have to see if it generalizes to other examples or just works on the training set. For this, we have the validation set containing new input and target samples. This is used to modify the neural network structure until it performs on new samples or examples sufficiently. Once we have a good neural network structure, we test it on the test set, another set with new samples or examples to test the performance. We start our program with importing the PyTorch library, and then we select the device we are going to use. So if you have a GPU on your computer, or if you're using, for example, Google Colab, you can set the device to CUDA. Or if you're using a normal computer without a GPU, you can set it to CPU. Then we define out our neural network with a linear layer and a nonlinear activation function, which we can comment out on the forward function if we want to test the network without the activation function. This is done as a class such that the network is an object which we can instantiate and initialize in the main part of the program. This is our first experiment, and here we are defining the class. So this is how we can, one of the ways we can build a model in PyTorch. Here we're using linear layer, so in features is equals to 2, out features is equals to 2, and we're using bias, so we are setting bias to true. Here in the forward section we see that the output just goes through this layer, and we're commenting out here, so we don't have an activation function in this first experiment. And here we can see that we comment, if we remove the comment, we can use the leaky relu or we can use the relu as activation functions. But for this first experiment, we are going to look just at what the linear layer is doing. So here we define our class, and in the main part of our program, we will generate the data for training and for validation. So here we are defining our training set. So we have 3 vectors, and there we use a PyTorch tensor. And this is how we have our data in PyTorch. They use tensors, and tensors need a special shape depending on the layers and depending on the input. And so you need to pay attention on how to set up the inputs and outputs and the layers and models in PyTorch. So here we are adding the first dimension for the batch. So we have our tensor, and we can see the shape now, 1 by 3 by 2. So we have 3 features, each 3 samples, and each sample has 2 features. So 1, 2, 2, 1, 1, 1, x0, x1, x2, and this is how we're doing an input for our training set. And our target, as we mentioned before, so we have 1, 0, 0, 1, and 0, 0, and we also prepare and reshaping, and we have that the input and the target now they have the same shape. Here we have batch, sample, and features, or the signal dimension. So here's 1 batch, 3 samples, and the signal dimension is 2. Observe that the validation input data contains a scaled version of the training set. Now we instantiate the model, define the loss function and the optimizer. So here is what we are doing. Our model we are instantiating. So this was our leannet. And here leannet. Here we defining our loss. So we are using the mean squared error loss function from PyTorch. So here we are defining our optimizer. We're going to use the stochastic gradient descent, and we will start with the learning rate of 0.1. So we have here our loss, and our optimizer has a parameter is learning rate 0.1. Here we also have 2 choices of optimizers. So here you can see that this add-on optimizer is comment out. So we can replace, we can try which one works better. Next, we let the optimizer do 10,000 update iterations. They are called epochs. So this is what we're doing for epoch in range of 10,000. So the Y predictions is the model of X, so the model produces prediction output. Here the prediction and target are compared by loss. So for every 100 we are printing the epoch and the current loss value. So we see that we start with a high loss, and our loss is decreasing until it's a very small value, and we see that there are no further decrease after a certain point. Here is typical for PyTorch experiments. We use this optimizer 0 grad, that the optimizer sets previous gradients to 0. Loss backward is the optimizer computes new gradients, and optimizer step, so the optimizer updates weights. Oh, this is very typical in a PyTorch experiment. We always have, so we have the forward that we defined in the model. We have here the 0 grad, we have the loss backward, and we have optimizer step. And here we ran our experiment, So finally, we'll print out the results on the training set and the validation set and the obtained weights. And we see here we have the loss in training was here, very small loss, but we see that the loss on validation set 0.5. So we see that we didn't do a very good job because it works really well on training, but it doesn't generalize well. So on the validation set, it's just a very high loss. So each time we execute it, it starts with a different random initialization. Hence, each time we get a different route that the optimization takes, and possibly different results of the optimization. If we get very different results, then it's a sign that optimization got stuck in a local minimum, for example. Observe that we obtain the desired output on the training set, but the output for the validation set doesn't look good. This is reflected by the loss values, as I mentioned before. We have very small value to the order of magnitude of e to the power of -12 on the training set, but 0.5 on the validation set, and this is a very big loss. So it demonstrates that we have a bad generalization. In our experiment number 2, we are going to modify our neural network structure, trying to obtain a better generalization. And we will do that by adding the activation function. So if we look at the code, we are uncommenting the leaky relu, and we are also uncommenting here so our output now is first goes to the first layer, which is the linear layer, and then we apply an activation function, which is the leaky relu. We will not make changes here, so we are still using the stochastic gradient descent optimizer. And here also we are not changing anything. We just run our model and we see that we have different results. So now the loss for our training set is 1.8 in the magnitude order of magnitude 10 to the power of -5, but we have the validation loss is 0.144. When we compare the previous experiment, it was 0.5. So we already have some good reduction on the validation set, meaning that our model is generalizing better. So here we get a loss. Our training set is a very small value. For the validation set, we get 0.441, so it's much better than before. So using this activation function helped for better generalization. In our final experiment, we are going to change the activation function. We are going to use the relu, and we will see the effect of vanishing gradients on the optimization. So this function has a constant 0 for negative values and hence a vanishing gradient for negative values. So what we do is now we are not going to use the leaky relu, we are going to use the relu. And here we didn't change in our forward part. We're still using the same optimizer, no changes here. And we see that we run our experiment, but we see that the loss gets stuck and is not changing after some time. And here we see that even in the training set, the loss is 0.166. So the optimizer gets stuck at a loss value of 0.166 to retrain, and this is caused by the vanishing gradient of the relu function in the negative input range. So with these 3 experiments, we've seen the effects when we are not using activation functions, when we are using an activation function, and we need to be aware of the characteristics of our data, the characteristics of our network architecture, and the characteristics of our optimizers. So there are thousands of parameters we can change, and we need to have a certain intuition on how to fine-tune our model to achieve the results we want.